Hello. So in this video we're going to talk about the first derivative test, and the idea here is to figure out whether you have a relative maximum or minimum, right, or a relative minimum. And we saw before, in a couple sections ago, that we look for our relative maximum or minimum points at critical numbers. Right? Because if you have a maximum or a minimum, a relative maximum or minimum, then you know it has to happen at a critical number. But not all critical numbers give you a maximum or minimum. And so how can we tell the difference, right? How do we know whether a critical number gives us a maximum or a minimum or neither? So that's the first derivative test, right? So before we get to that, just some terminology here. We have a function is increasing, right, on an interval I when, if you have x1 less than x2, so let me make that a little bit bigger here, right? Suppose we have x1 less than x2, right? Then that gives us that f of x1 is less than f of x2, right? For any x1 and x2 on the interval. Right. So, yeah, let's just draw it out. Let's draw the graph here. So we have our x and y plane, and we'll call this x1 down here, and then x2 has to be bigger than x1, and then let's say f of x1 is here, and then f of x2 has to be bigger than that, so that's up here. So here's one point on the graph, here's another point. To go from one point to the other, what do we have to do? We have to be going up, right? So we don't use the term going up, we say that the function is increasing. Right? So as the x values get bigger, the y values get bigger, that means that it's increasing. Okay. On the other hand, let's do this in a different color here. Suppose we have x1 still less than x2, but now f of x2, let's say f of x1 is bigger than f of x2. Right. For any x1 and x2 on your interval. So if we draw the picture here, so here's x1, do this in yellow. So here's x1. Here's x2, but now f of x1 is way up here, and f of x2 might be a little lower than that. So now we have the reverse picture here, right? So now our function has to be decreasing, going down, right? So this is decreasing, right? Okay, so that's just the definition. But as it turns out, there's a much easier way to determine whether a function is increasing or decreasing, rather than have to check all these pairs of points, these x1s and x2s. You got to check every pair. And you have to check that this condition is satisfied for every possible x1 and x2. That usually is not feasible, right? It's not possible to do that. It'll take forever. So, theorem 3.5 then, this theorem here, will give us a much easier way to determine whether a function is increasing or decreasing on a given interval. Right. And it just uses the derivative. It uses the first derivative. Right. So here's the idea. We have, again, this is just the definition of increasing and decreasing. Now we get to the theorem. which says the following, right? So we have a continuous function, right? So f is continuous on, let's say, a closed and bounded interval. And let's say it's differentiable on the open interval, so not including a and b, right? So part A says that if the function, or if the derivative of the function, right, if f prime of x is positive for all x in the interval, and let's say the open interval, then we know f is increasing. Again, on that specific interval. Right. So, right back up here where we see the function is increasing, what does the derivative mean? Or the derivative is the slope of the tangent line. So if I were to draw a tangent line at, let's say, this value of x here, the tangent line would look like this, right? And we definitely know the slope is positive there, right? So in other words, f prime of x would have to be positive. Makes sense? And so the reverse is true. If you take any x on your given interval and you look at the slope of the tangent line here, the tangent line will probably be doing something like this. And because it's going down, this is going to have a negative slope. So when the slope is negative, right, then we know that it's decreasing. Makes sense? Yeah. So when the slope is positive, that was the first example, then we know it's increasing. Right. But there's a third possibility. Suppose that the derivative is always 0. Right. So right. B, you can read up there. C, suppose that the derivative of the function is 0, not just at a single point, but for all x on the interval. So if the derivative is always 0, right, then the slope is always 0, which means your function has to look like this, right? It has to be a horizontal line. Because as soon as you have a little bump here, now your slope is no longer 0. It could be positive, it could be negative, but it's not going to be 0. It's got to be 0 everywhere, right? Right. Which means it's just a constant function, right? So f of x could be, 7, right? Or pick your favorite number, right? Any constant. Because we know the derivative of a constant is 0, right? So in this case, yeah, we just say f is constant. So it's not increasing, it's not decreasing, it's just flat, horizontal, constant. Okay, so that's the third statement here. Right, so yeah, if the derivative is always positive, you know it's increasing. If the derivative is always negative, you know it's decreasing. And if the derivative is always 0, then it's not increasing, it's not decreasing. We say it's a constant function, right? Okay, so now we want to determine where a function is increasing and where is it decreasing, because a function doesn't always have to be increasing. And I drew the picture. These pictures are functions that are always increasing or always decreasing. But of course, you can have a function that, looks like this. In which case, you can say maybe it's increasing here, and it's increasing here. But then, in between, from here to here, it's decreasing, right? So we want to determine what are the cutoff points, right? Where is it decreasing? And then where is it increasing? So we want to describe these intervals here, right? These are going to be intervals, you can say I, and typically we'll use just an open interval from, say, A to B. So we have to figure out where's our A and where's our B, right? So that's what we're going to do now. So, yep, so to find intervals where your function f is either increasing or decreasing. Decreasing, okay. Yep, it's just a three-step process, right? First thing we're going to do is find all critical numbers of our function. You remember what a critical number is, right? A critical number is where the derivative is either 0 or fails to exist. Okay, so find all critical numbers and all points of discontinuity. Right? So remember all holes, asymptotes, and jumps. Right? A jump, right, looks like this when a function jumps from one point to another. So I'll call that a jump. So yeah, so what, right? So at these points of discontinuity or at the critical numbers, the interval, right, it can change from increasing to decreasing or vice versa, right? And in the picture I drew here, at the very top here, the tangent line has slope 0, right, which means this x here is a critical number, and that's where it can change from increasing to decreasing, right? Or this critical number here, right, it changes from decreasing to increasing. So, right, so where it changes is where we want to find it, right? So once we find all the critical numbers and all the points of discontinuity, we just, right, take a number line. So we draw a number line, right, something like this, and then we mark off every point of either discontinuity or every critical number. So whether it's a point of discontinuity or a critical number, we'll just label them as C1, C2, C3, right? However many you have. You might have 4 of them, 5 of them. You can have infinitely many, but then usually in that case we restrict ourselves to a certain portion where there's just a few critical numbers. Okay, so once we do this, we have our intervals, right? We have this interval going from, well, from negative infinity all the way to C1, and then from C1 to C2, C2 to C3, and then C3 to infinity. So we might have 3 critical numbers or 3 points of discontinuity, but we have 4 intervals, right? So on each interval, we need to determine the derivative. Actually, we don't care what the derivative is. We just want to know the sign of the derivative, right? Whether it's positive or negative. Okay. And then based on that, well, let's say the derivative is positive on an interval I. Well, by this theorem up here, theorem 3.5, we know that the function will be increasing. Then f is increasing on that interval. Right. If the derivative is negative, less than 0 on that interval, then we know the function is decreasing. And it could happen, although there's not a lot of functions that do this, where the derivative equals 0 everywhere on the interval. You sort of have to, maybe for a piecewise defined function, you can come up with such a function, but they don't naturally occur, right? So for some piecewise functions, the derivative could be 0 everywhere, in which case f is constant on the interval. But again, that doesn't happen often. Okay, so this is how to determine where the intervals of increasing and decreasing are. Okay, so let's just do an example. Okay, so here's our first example. We're given a function. It's going to be x to the 5th minus 5x to the 4th plus 5x cubed plus 10. And we want to know, where is the function increasing, where is it decreasing, and where is it constant? Okay, so remember, step one is to find the critical numbers. So to find the critical numbers, right, we need to find, I'll call this step one here. We need to find the derivative. And that should not be hard at this point. You just use all the rules. So the derivative should be 5x to the 4 minus 5 times 4, so that's 20, x to the 3 plus 5 times 3, so 15x to the 2. And we want to know first, where does this function not exist? Well, it's a polynomial, right? It's going to exist everywhere, right? We're not dividing by 0, right? There's no square roots, there's no asymptotes, there's no jumps, right? It's a nice continuous polynomial. So the only critical numbers come from where this equals 0. So we have to solve that equation. And to do that, it might be helpful to notice that 5, 15, and 20 are multiples of 5, so we can factor out a 5. And we can also factor out the lowest power of x, x squared. So if we factor out 5x squared, we get x squared minus 4x plus 3. So you see where this is going, right? We're going to keep factoring. This x squared minus 4x plus 3 should be factorable as, I think, x minus 1, x minus 3. Right? So negative 1 plus negative 3 is negative 4. Negative 1 times negative 3 is positive 3, right? So what are the solutions? Well, there's going to be x equals 0, x equals 1, and x equals 3. So 3 critical numbers, right? These are all critical numbers. And that's it. Again, be careful. 5 is not a critical number, right? 5 is just a coefficient here. We can divide by 5. That's not a big deal. But if x squared is 0, then x equals 0. So 0 is definitely a critical number because, well, if you plug it in, you get 0 minus 0 plus 0, which of course is 0. So yeah, don't forget the 0 because the x squared is a factor here. Okay, so what's step 2? After you find the critical numbers, draw a number line. So here's my number line, and luckily these went in order here, right? So here's x equals 0, here's x equals 1, and here's x equals 3. So these are my 3 critical numbers. And they divide the line up into, well, 4 separate intervals, right? From negative infinity to 0, from 0 to 1, from 1 to 3, and then from 3 to infinity. Okay, so which ones are going to be increasing, which ones are decreasing? Well, that's going to be, that's still step 2, right? We have to basically plug in a number on each interval here into the derivative. So we have the derivative. In fact, I'm going to use this version of the derivative. It's easier. And pick a number that's less than 0. How about negative 1, right? Let's keep it simple. Plug that into the derivative. And what do we get? We get 5 times negative 1 squared times negative 1 minus 1 times negative 1 minus 3. So that's going to be 5 times negative 2 times negative 4. So I guess we get positive 40, right? Which is positive, right? 40 is greater than 0. So we know that the derivative will be positive at negative 1. But it's also going to be positive at negative 2 or negative 3 or negative 1/2. How do I know that, right? Unless I actually plug in negative 2, how did I know it's going to be positive? Well, right, the only place that it can change from, say, increasing to decreasing, right, is at one of these critical numbers, is at the dividing points, right? So, right, the only dividing points are 0, 1, and 3. So anything less than 0, there are no more dividing points. So the derivative will be positive everywhere x is less than 0. Right? So that means we know it's going to be increasing on this interval. What about between 0 and 1? What numbers between 0 and 1? Well, unfortunately, we're running out of nice numbers here, so we'll have to pick something like 1/2. Plug that into the derivative. And notice that x squared is always positive, right? So 1/2 minus 1 is negative. 1/2 minus 3 is negative. So I think this, whatever number this is, it's definitely going to be positive, right? It's a positive times a negative times a negative. So it's also going to be positive at 1/2, or 1/4, or 3/4, right? Or 1/3. It's going to be positive everywhere between 0 and 1. So it's going to be increasing between 0 and 1 as well. Okay. So what's between 1 and 3? Well, 2 makes sense. So if we plug in x equals 2, what do we get now? I think we just get negative 20. Right, so now we get a negative. So it's going to be negative at positive 2. It's going to be negative everywhere between 1 and 3. So this is where it's going to be decreasing. Right. And finally, pick your favorite number bigger than 3. So I'll just use 4. Plug that into the derivative here. And now I think everything is positive. So whatever number that is, it's a positive. So now we're back to positive. And so when x is greater than 3, we're going to be increasing. So to answer the question, that's step 3 here. Right. So f is going to be increasing. Now, we have to be careful in general, right? Because it looks like it's going to be increasing all the way from negative infinity and then up until 1. So what about 0? 0, right? Remember, the derivative is going to be 0 at 0. Same thing at 1 and at 3. Right? So even though the derivative at 0 is 0, what's going to happen for the graph is it's going to kind of level off and then just go back up. So the idea is it's still going to be increasing. If I pick any two x's, say x1 and x2, you can compare the y values. F of x2 will be slightly bigger than f of x1. So that's going to be true at least up until we get to x equals 1. That's where it changes to decreasing. Again, I'm not going to draw the graph here just yet, but that's the idea. So here we can go through 0, and we can say that it's increasing from negative infinity to 1, but it's also going to be increasing from 3 to infinity. So anywhere you see a positive sign or a 0, right, that's where it's going to be increasing. Where is it going to be decreasing? Well, everywhere we see a negative sign, and that's everywhere between 1 and 3. So just on the interval from 1 to 3, and that's it. Okay, so that's everything, right? Where is it constant? It's not, right? So where is it constant? Nowhere. It's either increasing or decreasing, right? So yeah, I probably shouldn't even ask that, but as I said earlier, f is constant, usually nowhere. Nowhere. Right. So that answers these 3 questions here. Okay, so yeah, so be careful. When you have a critical number, it's very likely that the signs will change, either from negative to positive or positive to negative, which means that's where it changes from increasing to decreasing or decreasing to increasing. But just because you have a critical number doesn't mean it does change. Notice that at 0, it doesn't change, and that's why we can skip over 0 here. And I should mention, if you say from negative infinity to 0, and then from 0 to 1, that's okay too. That's okay too. And in some cases, you have to do that, depending on the nature of this point. This is, right, as I mentioned in the graph, it just levels off there. But if you have, let's say, a vertical asymptote, right, you can have a vertical asymptote, and the graph might just do this. It might be increasing here, and then it might be increasing here, which means it's not increasing, right, from this point to this point, right? So we cannot conclude that it's increasing everywhere, right? Let's say that this is x equals, 7. It's increasing from negative infinity to 7, and then again from 7 to infinity, but we cannot say it's increasing from negative infinity to infinity for the reason I just mentioned, that this point here is higher than this point here. So we're not increasing, we're decreasing, right? So yeah, we can't skip over the 7 here in this case, right? We skipped over the 0 in this case because there's no asymptote, there's no jump. Okay, so I hope that helps. Yeah, so maybe we'll do one more example, and then we'll move on to the first derivative test. Okay, so we have another function. G of x is cosine squared minus cosine, right? And we're only going to look between 0 and 2 pi, right? Remember, 0 to 2 pi is effectively one complete period of the cosine function. Now, because of the cosine squared, it might be more than one period, but that's okay, right? It's a finite interval, so there's only going to be a finite number of these places where it changes from increasing to decreasing, or vice versa, right? So yeah, you'll see that in step 1, there's only a finite number of critical points, because if we went from negative infinity to infinity, well, then we're going to have an infinite number of critical numbers. So we're only looking from 0 to 2 pi, just because after 2 pi, from 2 pi to 4 pi and so on, they're just going to repeat themselves. Okay. So step 1, right? Find the critical numbers. So we need the derivative. So the derivative of cosine squared is 2 times cosine, right? Chain rule, times negative sine, right? And then the derivative of negative cosine is positive sine of x. So, yep, this is negative 2 sine x cosine x plus sine x. And just like the first example, right, there's no asymptotes here, there's no jumps. This is a nice continuous differentiable function. So the only critical numbers are where this equals 0, right? So we have to solve this equation. And some of you might be thinking, oh, this looks familiar. This looks like sine of 2x, right? This looks like the double angle formula. Yes, but I don't think that's going to help us here. What's going to help us is the fact that there's a sine here and a sine here. So it's a common factor, right? We can factor out sine of x, and it multiplies negative 2 cosine of x plus 1. And so now that we have the two factors, we just set the two factors equal to 0. So sine of x equals 0, and then, well, this is 1 minus 2 cosine x equals 0. So you should know where sine is 0. That's going to be at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. But at least between 0 and 2 pi, it's just these three numbers here, right? All right, what about 1 minus cosine of x, or 1 minus 2 cosine of x equals 0? Well, this just means cosine of x is 1/2. And if you remember your unit circle, cosine is going to be 1/2 at either pi over 3 or negative pi over 3. However, negative pi over 3 is less than 0, so we don't want to go clockwise here, right? We don't want this angle. We want to go counterclockwise. So we want this to be a positive angle. And in that case, this will be 5 pi over 3. Okay, so this equation has two solutions, pi over 3 and 5 pi over 3. So altogether, it looks like we have 5 critical numbers. However, notice that the 0 and the 2 pi here, the 0 and 2 pi are the endpoints. There's nothing to the right of 2 pi, there's nothing to the left of 0. I mean, well, of course there are numbers bigger than 2 pi, but we're not considering those. We're only looking between 0 and 2 pi. So effectively, we can ignore the 0 and the 2 pi here because those are the endpoints, right? It's not going to change from increasing to decreasing at the endpoint, right? It's sort of the, the furthest left we can go, the furthest right. They're the barriers, right? So yeah, so for step 2, we'll draw the number line here, right? And we can stop at 2 pi. We're not going any further than that, and we can stop at 0. Okay. So what are the critical numbers? Well, there's pi over 3 right about here. Oh, it's even smaller than that. Pi over 3 is right about here. There's pi, so we have to go in order here. Here's pi, and then 5 pi over 3 is somewhere over here. Right. So if you want to include 0 and 2 pi, right, as your critical numbers, that's fine, but you're not going to plug in anything to the right of 2 pi or to the left of 0. For our purposes, there's nothing there, right? So, yep, 3 critical numbers, pi over 3, pi, and 5 pi over 3. Right, so that's where the derivative will be 0. Right, so this is the derivative of g. So we just have to plug in numbers on each of these intervals. So, yep, let's pick your favorite number between 0 and pi over 3. Yeah, be careful. Pi over 2 is bigger than pi over 3. So that might be a good one for the next interval, but here you can pick pi over 4, pi over 6. We'll do pi over 4, let's say. So let's plug in pi over 4 into the derivative of g. And, well, here's the derivative, g prime of x. Again, it's helpful to use the factored version. You could go back to the original version here, but it doesn't, it's not. You're going to get the same answer either way, right? Right. So let's see, what do we get? We get sine of pi over 4 times 1 minus 2 times the cosine of pi over 4. So we know sine of pi over 4 is positive. Just square root of 2 over 2. Cosine of pi over 4 is also square root of 2 over 2. But then when you multiply by 2, you just get 1 minus the square root of 2, which is definitely negative, right? It's negative 0.414, I think. Don't quote me on that. So square root of 2, oh gosh, and then 1 minus that, it's, okay, it is negative 0.41. Yeah. The fact is it's a positive times a negative, so this is definitely negative. So that's where it'll be decreasing. All right. So what about between pi over 3 and pi? Well, I already hinted at pi over 2. That's a good one to try. So plug that in to the derivative, right? Don't plug it into the original function. That does not tell you the slope, right? That doesn't tell you whether it's increasing or decreasing, right? That will tell you whether it's above the x-axis or below. If y is positive, you're above the x-axis. If y is negative, you're below the x-axis. But it doesn't tell you, right, if you're above the x-axis, it doesn't tell you whether you're going down or whether you're going up. So, yeah, that's why we need to plug it into the derivative here, right? Right, so what do we get? We get sine of pi over 2 times 1 minus 2 times the cosine of pi over 2. So sine of pi over 2 is 1. Cosine of pi over 2 is 0, so 1 minus 0 is 1, so we just get 1. And 1 is definitely positive. So here it's going to be positive. And then between pi and 5 pi over 3, You have a lot of good choices there, like 2 pi over 3, or even 3 pi over 2 is good. So if you plug that into the derivative, 3 pi over 2, I think the sign will be -1 there. And 1 minus 2 times the cosine of 3 pi over 2 is again 0. So you're just going to get -1 times 1, which is -1, which is negative. So now it's going to be negative. And, well, at this point you could probably guess what happens between 5 pi over 3 and 2 pi. So what can I plug in here? I guess I can plug in 7 pi over 4. Or you could do 11 pi over 6. Those are the two nice numbers. And let's see, the sine of 7 pi over 4 is going to be negative square root of 2 over 2. And the cosine will be positive square root of 2 over 2. So I guess we get a negative times a negative, which is positive again. So, yep, in this case, they do all alternate. Yeah, it doesn't matter what it equals, as long as you know whether it's positive or negative. Okay, so now we can answer the original question. The function g is going to be increasing on which intervals? Well, where you see a positive sign, right? So from pi over 3 to pi, and then again from 5 pi over 3 to 2 pi. So pi over 3 to pi, union 5 pi over 3 to 2 pi. And then g will be decreasing everywhere else. Right, so that's from 0 to pi over 3, and then from pi to 5 pi over 3, right? Okay, and that's it, right? Notice I didn't even ask where is it constant, right? You know by now that sines and cosine functions just go back and forth like this. So it's never going to be flat or horizontal. So it's not constant anywhere. Okay. Oh, also notice that all of these intervals are open intervals. When you're describing increasing or decreasing or constant, always use open intervals. Right. In other words, parentheses, no brackets, right? Even though in the original question, right, this was the closed interval. Notice at 0, we're including 0 in the domain of the function, but notice I did not have a bracket around the 0 here. Okay. So yeah, when you're describing increasing or decreasing, always use open intervals, not closed ones. Do not use a bracket anywhere, right? And the reason is because, well, look at pi over 3. Where would you put the bracket, right? Would you put the bracket here or up here or both? So think about pi over 3. Here's your x, right? Here's your function g of x. So at pi over 3, we have a point on the graph. And I don't remember what point it is. Let's see. So cosine of pi over 3 is 1/2. So we get 1/2 squared is 1/4 minus 1/2. So you actually get negative 1/4. So I was wrong. It's not above the x-axis. It's below the x-axis. So yeah, so down here. So this is the point pi over 3. X is pi over 3. Y is negative 1/4. Right. So what's happening at pi over 3? Is it increasing? Is it decreasing? Right. There's no way to tell. If you just have a point, a random point, there's no way to tell whether it's increasing or decreasing. right? The only way to tell is to look at other points. If we knew the graph looked like this, it's a sloppy graph, but let's say it looked like this. Well, now we can say that the function is increasing at that point. But at the same point, the function might also look like this, in which case you would have to say it's decreasing. So if you just have a single point, there's no way to determine whether it's increasing or decreasing. So that's the reason why we don't use brackets here, why we don't include the endpoints. Right? So yeah, so what's happening here, of course, is at pi over 3, the graph will look something like this. So yeah, it's not increasing or decreasing at this point, because this is where it changes from decreasing, right, to increasing at pi over 3. So at pi over 3, it's not doing anything. It's not going up. It's not going down, right? So in fact, you can see it's going to be a relative minimum. And that's what we're going to do next, right? So yeah, the endpoints of these intervals are always not included. They're all open intervals. And that was true for the first example we did. You might want to look at that again. I did not use any brackets when describing the intervals of increasing or decreasing. Okay, so now we come to the main topic for this section is the first derivative test. So the first derivative test is it's a test to determine whether a critical number gives you a maximum, a minimum, or neither, right? And so you can see those are the three possibilities here, right? So we have C is a critical number. C is a critical number for your function f. And remember what that means. It means that the derivative of f at c is either 0 or it does not exist. Either way, it's a critical number. Right? On some interval containing c, right? So here's the picture. Here's your c. Let's say from here to here is your interval. Right? And so here's the idea, right? When you were making your little sign charts for determining where your function is increasing or decreasing, right? So let's suppose that the derivative is negative here and then positive here. So what's happening? The graph is decreasing and then increasing. So what happens at C? You have a relative minimum. Right? So the first derivative test says if you look at points to the left of C, plug them into the derivative. Right? If the derivative there is negative, and then you plug in points to the right of C, bigger than C, and if the derivative there is positive, then you know you have a relative minimum at C. So, right. So this will be your relative minimum. Right. And in this case, right, we know that the derivative is 0 because you have a nice tangent line here. But that's not the only possibility, right? Your graph might actually look like this. In which case, we still want to say that this is a relative minimum, but now there's no derivative at C. Right? The derivative does not exist. There's no tangent line. Right? This is not the tangent line because it's not smooth there. Right? So yeah, that's also a possibility. It doesn't have to be a nice smooth graph. Right? Okay. Oops, sorry. Minimum. Right. So yep. So that's the first possibility here. The second. Do it over here as well. So here's your C. But now suppose that the derivative is going to be positive to the left of C and negative to the right of C. So that means the graph will be increasing when x is less than C, and it's going to be decreasing when x is bigger than C. So now, at x equals C, this point here will be a relative maximum, right? Because it's the highest point nearby, right? So that's the second possibility. Yeah, so this, yeah, it's over here. This is the second possibility. Erase this 2 here. Instead, I'll make this the third possibility, right? If the sign of the derivative doesn't change. So for example, if this is your c here, and let's suppose the derivative is negative to the left and negative to the right. In fact, I think we saw an example of that already where the sign of the derivative does not change. So the graph then will look something like this. It could be decreasing, 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 and then at c the derivative may be 0 here, but then it's still going to be decreasing. So if the graph looks like this, then at c, at this point right here, I would not call that a minimum, right? Because there are points lower than it, very nearby. I would not call it a maximum. There are points higher than that, very nearby. So it's not a minimum. It's not a maximum. Sorry. It's neither, right? So here, this is neither a relative minimum nor a maximum. Right. And it didn't matter that the derivative was negative, right? Suppose the derivative was positive, both to the left and to the right. Now the graph might look like this, in which case at c itself, at this point here, again, not a minimum, not a maximum. It's neither. Okay, so those are the three possibilities, right? Okay, so let's look at our first example. Okay, so we have a function, 20 minus 45x plus 12x squared minus x cubed. And we want to find all relative maximum and minimum points on the graph, right? So how do we do that? Well, we're going to use the first derivative test, right? So our relative maximum minimum points have to occur at critical numbers. So we need to find the critical numbers first. Right. Now this is a polynomial, right? So the domain is all real numbers. So we have to look for any critical number anywhere, not just on a specific interval, right? So find all the critical numbers. So to do that, we take the derivative. And what do we get? We get 0 minus 45 plus 24x minus 3x squared. And I know that's backwards, so maybe let's just write it the correct way here. Negative 3x squared plus 24x minus 45. Again, the derivative will exist everywhere. So the only critical numbers then come from where the derivative equals 0. So of course we have to solve this quadratic equation. And you could do it any way you want. You can use the quadratic formula. I'm going to factor out the negative 3 first. If it's okay with you. Plus 15, yep. So I recognize we can factor this as x minus 3 times x minus 5. So we get x equals 3 and x equals 5 as our critical numbers. Okay, and you'd get the same two numbers if you use the quadratic formula. Remember, negative 3 is the coefficient. That's not a critical number, right? So it's only two critical numbers, right? 3 and 5. So draw a number line. Mark off the 3 and the 5 here, right? And again, this will be, the domain is all real numbers, so it goes to the left and right forever. And now we're just going to plug in numbers into the derivative. Here we can't forget the negative 3 now, right? So let me copy this down here, right? So f prime of x is negative 3 times x minus 3 times x minus 5. If you'd rather use, this version, that's okay too. But it's easier for me to multiply numbers like this than to have to add and subtract them all. Okay, so let's start with the first interval here. Pick your favorite number less than 3. So I like 0. If you plug in 0 into the derivative, you just get -3 times -3 times -5, which is -45, right? So now we know the derivative is negative when x is less than 3, right? So it'll be decreasing on that interval. And pick your favorite number between 3 and 5. Well, there's 4. I mean, you can pick, 3.8, 4.7. You can pick pi, right? You can plug in 3.14159. But let's keep it simple. Let's just plug in 4. So -3 times 4 minus 3 times 4 minus 5. So that's just going to be +3, right? So that's going to be positive. And finally, pick your favorite number bigger than 5. So 6. 6 is good. Plug that into the derivative. Oops. 6 minus 3, 6 minus 5. So I think we get -3 times 3 times 1. So it's going to be -9, which is negative. Yep. Okay. Oh, so there was a shortcut here. If you don't want to plug in all these numbers, right, you don't have to plug in all of them. You do have to plug in 1, right? So let's say we plugged in 0 into the derivative, and we found that this is negative here, right? You can stop there, right? So look at the exponents, right, of the factors of the derivative. Here we had an exponent of 1. Here we had an exponent of 1. Right? When the exponents are odd, the signs have to alternate. Right? So if we did get a negative here, then we know that it's going to be positive and then negative without having to plug in the 4 and the 6. Right? Yep. On the other hand, if you get an exponent of, say, 2, then that's an even number. And in that case, the signs will not change. If you go back to our very first example, right, where we had a factor of x squared, you'll remember that at 0, I think it stayed negative, right? It went from a negative to a negative. Now I'm forgetting. I think it was a positive and a positive, wasn't it? Let me go back. Yeah, it was positive to positive. Right? So yeah, when the exponent is even, the signs do not alternate. The signs will stay the same. But when the exponents are all odd numbers, right, like 1, and this was a 1 here, so let me get rid of the 2. That was a what if situation. Right? The exponents here, of course, are just 1s. Right? Not derivative symbols, just 1s, right? Not primes. Okay, so right now we know where the function is increasing or decreasing, but really now we just want to go back and use the first derivative test because we want to know where do we have a maximum, where do we have a minimum. Well, if you look at the graph here, we're going from a negative to a positive, so the function will be decreasing then increasing. So that's the telltale sign of a minimum, right? So we can check the first derivative test. Yep, when you're going from a negative to a positive, left to right, negative to positive, you have a relative minimum. So, right, so f has a relative minimum at x equals 3. Now, remember, they wanted the minimum points, right? Remember, a point is not a number. It's a pair of numbers, right? It's an x and a y. So how do you find the y? Let me try that again. That 3 looks weird. Okay, so x is 3, y is what? So y is just going to be f of 3, but f is the original function. Don't plug it into the derivative. You got to plug it into the original function up here. Okay, so that's just using a calculator. So what is that going to be? That's going to be 20 minus 45 times 3 plus 12 times 3 squared minus 3 cubed. I get 29. I hope that's right. So that's the y-coordinate, and that's your relative minimum point. Okay. So what happens at 5? Right, because 5 was also a critical number. So at 5, the graph is increasing and then decreasing. That's the sign of a maximum. Right. So f has a relative maximum. At x equals 5, y equals, again, you gotta plug it in. Well, my notes say 75, and so if my notes are wrong, let me know. But I think that's where you have a relative maximum. Okay, so one minimum, one maximum, and of course the graph just does this. Right. So, yep, this is your relative minimum, 329. This is your relative maximum. And notice that neither one of these is an absolute maximum or an absolute minimum, but they are relative maximum and minimums, right? A relative maximum is just the peak of a hill, and the relative minimum is a valley. Okay, so that answers that. That's where we have a relative maximum and relative minimum. So that's how this goes. Maybe I'll do one more example. Scroll down here. Yep. Okay, so we have a function 2x squared minus x plus 7 all over x minus 1, and find all relative extrema. So the book uses the word extrema sometimes. Extrema just means maximum or minimum. Right. So highest point, lowest points, extreme points, right? Okay, so we do it the same way. The first step, of course, is to find the critical numbers. Because when you have a relative maximum or minimum, they have to occur at a critical number, right? Now, not all critical numbers will give you a relative maximum or minimum, but that's where we look for them, okay? Because that's where they have to be. They have to be at a critical number. So what do we need? We need the derivative. Now, this is not a polynomial, right? This is a rational function, which means when we take the derivative, we'll have to use the quotient rule. So low d high minus high d low. Yep, so denominator times the derivative of the numerator minus numerator times the derivative of the denominator, which is 1, and then divided by the denominator squared. So let's see, multiplying all this out here. Oh, I guess I better do it, right? So what are we going to get? We're going to get 4x squared. Minus 4x minus x is minus 5x, and then plus 1. And then minus 2x squared plus x minus 7. Again, all over x minus 1 squared. So I think we get 2x squared minus 5x plus x is minus 4x, and then 1 minus 7 is negative 6. And I think we can do one better. We can certainly factor out the 2 in the numerator. And we can factor x squared minus 2x minus 3. So it's x minus 1 times x plus 3. Oh, no, I got it backwards, right? Positive 1, negative 3. 1 minus 3 is negative 2, right? there we go, over x minus 1 squared. So that's the derivative. Right? That's my f prime of x. Right? So now remember, a critical number is where the derivative is 0. So where does this equal 0? When the numerator is 0, which means x is negative 1 or positive 3. Right? So two critical numbers, negative 1 and positive 3, right? Now don't forget, a critical number is also where the derivative does not exist. Notice the denominator here, right? The denominator is 0 when x is 1. So if I plug in 1 into the derivative does not exist. Right? So is x equals 1 a critical number? Did I miss that? Technically, no. X equals 1 is not a critical number. Why not, right? The derivative does not exist at 1. And that's part of what a critical number is. But remember, a critical number has to be part of the graph of the function. So if you go back to the original function, if you plug in 1 there, you're still going to be dividing by 0. F of 1 is undefined. So in other words, there is no point on the graph corresponding to x equals 1. So for that matter, it cannot be a critical number. It cannot be a critical number. However, it is a vertical asymptote, right? So x equals 1 is a vertical asymptote. It is a point of discontinuity. Right? Which means when we draw our number line here, right, in step 2, right, draw a number line. We have negative 1 here on the left. We have 3 on the right. Right? But we also have to include 0, even though it's, sorry, not 0, 1. We have to include positive 1, even though it's not a critical number. Right? Here the derivative is 0, here the derivative is 0, here the derivative is undefined, but then again, so is the original function. Okay. So yeah, when you have an asymptote, right, when you have a vertical asymptote, let's say this is your asymptote, notice what can happen. The sign of the derivative could change. Right? If this is the graph here, we're going from increasing to decreasing. Even though at x equals 0, there's no, there's no maximum, right? And there's no critical number at 0. But the sign of the derivative could still change there. So that's why we have to consider x equals 1 when looking at where the sign changes, right? Okay. Oh, let me replace the u here for undefined. Right. Okay. So now you do the usual thing. You plug in numbers into the derivative. And where should we start? How about negative 2? If you plug in negative 2 into the derivative, and the derivative is up here, what do we get? We get 2 times negative 2 plus 1 is negative 1. Negative 2 minus 3 is negative 5. And then the denominator will always be positive, right, because you're squaring it. So it looks like 10 divided by 9, which is definitely positive. So it's going to be increasing at negative 2. How about at 0? If we plug in 0, so look at the signs, right? I'm going to do the shortcut here. At negative 1, the exponent was a 1, and that means the signs have to alternate. So this will be negative here. What about if you plugged in 2 into the derivative? Will it be a positive or a negative? So notice what happens at x equals 1. At x equals 1, the exponent is a 2. 2 is an even number, so that means the sign should stay the same. The sign will not alternate at 1. Right? Again, if you don't believe me, then okay, just plug in 2, right? I think we get negative 6 over, well, we get negative 6, right, which is negative. Okay. So what happens at 3? Again, the exponent of x minus 3, right, was 1, which is odd, and that means the sign here alternates as well. So as it happens, the sign did not alternate at the vertical asymptote, at the point of discontinuity, right? But it could have, so you have to be aware of that, right? So to answer the question, well, at negative 1, right, so now we're only looking at the two critical numbers, the negative 1 and the 3. At negative 1, we change from a positive to a negative. So that tells me we have a maximum. And at 3, we're going from negative to positive. So that tells me we have a minimum. So a minimum at 3 and a maximum at negative 1. So again, so we'll say that f has a relative maximum at x equals negative 1. Oh, and what's y going to be? Plug it back into the original function, and I think you'll get negative 5 for the y-coordinate. Likewise, f has a relative minimum at 3. 11? I think we get 11 here. Yep. Okay, and that's it. Again, one of each. Now, that's not always going to happen, right? You could get two relative maximums. You can get two relative maximums, one relative minimum, right? You might get, you might get 8 relative maximums and only 3 relative minimums. It really depends on the function. But if you get 3 critical numbers or 4 critical numbers, then, you might have more than one of each. So just be aware of that. And maybe we'll do one more example to show you that, you can definitely get more than one of each type. Okay. The one thing that, I erased the other two. But if you go back to the other two, you might have wondered, well, in the previous example, I think, or maybe it was the first example, we had something that looked like this, right? And here was your relative minimum. Here's your relative maximum. Let me go back to that. Yeah, I think this was 329, and this was 575. And if you're wondering, why did we have to go through any of this, the first derivative test, when all I had to look at were the y-coordinates? 75 is bigger than 29. So you can't have a minimum that's lower than 29, right? Then that had to be the maximum, and 29 is the smaller number. So 29 had to be where you have a minimum. So if you think it's that simple, that just look at the y-coordinates, the bigger number tells you that it's a maximum, and the smaller y value tells you you have a minimum. But no, look at this example here. If all you went by were the y-coordinates, 11 is bigger than negative 5, right? 11 is certainly bigger than negative 5. That might lead you to conclude that this is where you have a maximum, and that at negative 5 you'll have a minimum. But notice, that's not what we got. That's backwards, right? So you cannot just look at the y-coordinates and say, oh, well, 11 is bigger than negative 5, so 11 has to be the maximum. Nope. Not that. That does not happen here. So yeah, unfortunately, for better or worse, this is the procedure, right? Once you get used to it, it's really not that bad. Take your derivative, find the critical numbers, mark the critical numbers on your number line, and include any points of discontinuity, even though they're not, critical numbers. But the sign of the derivative could change there, so that might make it confusing, right? Yeah, and then, just use the first derivative test to test whether the critical number gives you a maximum or a minimum, right? Or neither, right? Obviously, if one were a critical number here, then this would be neither, right? It wouldn't be a minimum or maximum. But that's not what's happening, right, with the graph. The graph literally has a vertical asymptote like this. So, yeah. And in fact, if you looked at the graph, you'll see that it doesn't look anything like this. Maybe I'll do a quick rough sketch of the graph here. So here's 1, here's the asymptote at x equals 1, here's 3, and here's -1. So the graph, I think, will look something like this. Oh, sorry, it's negative, right? Yeah. So so something like that. And then up here, again, vertical asymptote, and something like this. It's a horrible looking graph. I don't know why that's doesn't look right to me. Oh, because I got it backwards. That's not how it looks. Right. You have a maximum at 1. So that's down here. There we go. Now it's right. And then at 3, you have a minimum. So this is a relative minimum. This is a relative maximum. Right? Even though this point is higher than this point, that is clearly not a maximum, right? It's a valley. It's the low point nearby. And over here, this is the high point nearby, right? So yeah, don't look at the y-coordinates. You have to go through the first derivative tests. Okay, so anyways, that's the first derivative test and how to use it to determine whether you have a relative maximum or relative minimum. Oh, I guess I promised one more. All right, one last example. Okay, so here's one with a trig function in it. F of x equals x plus 2 cosine x. And we're only going to look for the relative maximum and minimums on this interval from 0 to 2 pi. Okay, so remember, when you see a cosine function, it's going to look like this. And so where are your relative maximums? Well, they keep going, right? There's going to be an infinite number of them. And likewise, there's going to be an infinite number of relative minimums. So rather than find all of them, all infinitely many of them, we're just going to concentrate on one period of this. I think it's one period or so. Oh, it's not a periodic function. Never mind. Well, we're only looking at this piece of it, that portion of the graph from 0 to 2 pi. Right. So we're looking for the relative maximum and relative minimum points. So what do we need? The critical numbers. So take the derivative. Right? And yep, no asymptotes here. This is a nice trig function. Well, it's a sine or cosine function, which we know are continuous and differentiable everywhere. So here the only critical numbers come from where the derivative is 0. So you just have to solve this equation. Sine of x is equal to 1/2. So go back to your trigonometry days, your unit circle, and remember sine is the y-coordinate, so where is y 1/2? At this angle here, this is pi over 6. And then again over here at 5 pi over 6. And that's it from 0 to 2 pi, right? Obviously we can do 13 pi over 6. We can do 17 pi over 6, but those are bigger than 2 pi, right? So again, I think we only have the two critical numbers, pi over 6 and 5 pi over 6. I'm guessing we're going to get one of each, but okay, that happen. That can happen. Yep. So, am I missing any? 1 minus? No, I think that's it. Right. So two critical numbers. And now we just draw our number line, except it doesn't go on forever here, right? We're only going from 0 to 2 pi. Let me try that again. So we only need to go from 0 to 2 pi. No arrows here. And let's mark off the two critical numbers, pi over 6 and 5 pi over 6. So there's only 3 intervals here, right? From 0 to pi over 6, from pi over 6 to 5 pi over 6. And this is not to scale, obviously. I messed that up. Oh well. Look, it doesn't matter, right? As long as you have the 3 intervals. The 5 pi over 6 should be way over here. But let's not worry about that, right? So, plug in a number on each interval from 0 to pi over 6. Well, unfortunately, we don't have nice numbers here, so what can we plug in? Pi over 10, pi over 8 maybe. So you're not going to get a nice number here. And in fact, cosine of pi over 8, I don't know that by heart either. So this is where you're just going to have to break out your calculator and plug these numbers in and just see whether it's positive or negative. And don't do that because that's not the derivative. Oh, sorry, I was plugging this into the original function. Oops, never mind. Yeah, we're plugging it into this, the derivative, right? So this is just 1 minus 2 times the sine of pi over 8. And again, I don't know what the sine of pi over 8 is, but that's what we'll plug into the calculator here. And I get positive 0.2346. Okay, so as long as it's positive, that's good enough. Right, so so we're going to be positive on this interval. And then, wow, we have a big range here from pi over 6 to 5 pi over 6. We can plug in, pi over 2. And remember, sine of pi over 2 is 0. So this is, oh, wait a minute. Sine of pi over 2 is not 0. Sine of pi over, I should write that down. Sine of pi over 2 is 1. So this is 1 minus 2, which is negative 1. Right? Yep, so that's going to be negative here. And everywhere in between, right? And then what's bigger than 5 pi over 6? Pi is good. So 1 minus 2 times the sine of pi. Now sine of pi is 0, so 1 minus 0 is 1. And now we're back to positive again. So there we go. First derivative test says that we have a maximum at pi over 6 and a minimum at 5 pi over 6. So relative maximum at pi over 6, and then, so what's the y-coordinate is going to be, well, pi over 6 plus 2 times the cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. So, yeah, pi over 6 plus square root of 3 for the y-coordinates. Right, and that's your maximum. F has a relative minimum at 5 pi over 6. And then, let's see, 5 pi over 6 plus, so cosine of 5 pi over 6 is actually negative square root of 3 over 2. So now we subtract square root of 3. So those are the y-coordinates. Oops, didn't mean to cross that out. Again, when it asks for the relative extrema, to be on the safe side, I would find both the x and the y. If the question specifically says that you have a relative maximum at x equals, then you just have to find the x, right? The pi over 6 and the 5 pi over 6. Right. So in some cases, I'll just ask for the x coordinates, not the y coordinates. But the maximum value would be pi over 6 plus square root of 3, and the minimum value would be 5 pi over 6 minus square root of 3. So I hope that helps. And yeah, I guess that does it for the first derivative test.